cat falls from a New York apartment balcony, 27 stories high. As it plummets toward the concrete below, something remarkable happens. The cat twists, contorts, and somehow rights itself in midair. When it strikes the ground, it lands squarely on its feet, walks away with minor injuries, and lives to tell the tale. This is not fiction. It is a documented case from 1984, verified by veterinarians who treated the feline survivor. How is this possible? The physics seems impossible at first glance. The cat had no external forces acting on it while falling. No surfaces to push against, nothing to grab. It was in free fall, where the laws of physics dictate that angular momentum must be conserved. Yet somehow, starting from any orientation, a falling cat manages to rotate its body to land feet first. This defies our intuitive understanding of motion and rotation. For centuries, this feline ability remained one of nature's most perplexing mysteries. The cat-riding reflex, as it came to be known, challenged physicists, biologists, and mathematicians alike. It became more than just a curiosity about household pets. It evolved into a profound question about the fundamental laws of physics and whether exceptions could exist in nature's rulebook. This is the story of how humanity unraveled the physics of falling cats, a journey spanning over 150 years of scientific inquiry, cutting across multiple disciplines, and eventually leading to revolutionary insights that would transform robotics, space exploration, and our understanding of motion itself. The answer, when it finally emerged, would reveal not a violation of physical law, but something perhaps more astonishing. A clever exploitation of physics that had remained hidden in plain sight. And it all began with a simple question that confounded the greatest scientific minds of the 19th century. How does a cat always land on its feet? The mystery first entered the scientific literature in 1854, when physiologist James Clerk Maxwell, better known for his equations of electromagnetism, dropped cats from various heights and observed their uncanny ability to reorient themselves. But the formal investigation began in earnest in 1894, when the French scientist Étienne Jules Méry employed a revolutionary new technology, chronophotography. Méry, a pioneer in motion capture techniques, used a camera capable of taking 60 consecutive photographs per second to document the fall of a cat. The resulting images, a series of ghostly white cat silhouettes against a black background, became the first scientific documentation of the cat-riding reflex. They showed something extraordinary. The cat's body seemed to twist in the middle, with the front and rear halves rotating in opposite directions. "It is a puzzle that has vexed me considerably," wrote Méry in his notes. "The creature appears to violate Newton's laws, yet we know this cannot be possible." The images circulated throughout European scientific academies, catching the attention of physicists who immediately recognized the paradox. If a cat starts falling with no rotation and ends up rotated 180 degrees, where did this angular momentum come from? The law of conservation of angular momentum, a fundamental principle in physics, states that a system's total angular momentum remains constant unless acted upon by an external torque. In space, an astronaut who begins spinning can only stop by pushing against something else or by throwing part of their mass outward. A cat in free fall has nothing to push against. Yet Méry's photographs clearly showed cats accomplishing this seeming impossibility. Professor Richard Stanford, a physicist at Cambridge University, became obsessed with the problem after viewing Méry's photographs in 1896. "There must be a mechanical explanation," he wrote to a colleague. "Either the cat is pushing against air resistance, which seems insufficient for the rapid rotation observed, or it has discovered some loophole in our understanding of rotational dynamics." Stanford conducted his own experiments, dropping cats onto cushioned surfaces and attempting mathematical models of their motion. But the mathematics of the time proved insufficient to fully capture the complex, coordinated movements. Meanwhile, across the Atlantic, American biologist Natalie Brennan approached the problem from a different angle. Rather than focusing on the physics, she studied the anatomy of cats, particularly their flexible spines and specialized vestibular systems, the biological equipment that might make such feats possible. "The feline spine contains more vertebrae than our own," Brennan noted in an 1899 paper published in Scientific American. "This, combined with minimal collarbone structure, allows for extraordinary rotational capabilities between the front and rear portions of their bodies, a capacity humans simply do not possess. The mystery deepened when, in 1904, German physicist Arnold Sommerfeld pointed out another aspect of the paradox. If the cat truly had zero angular momentum at the beginning of the fall, as the conservation law would require, then it must maintain zero angular momentum throughout. So if the front half of the cat rotates one way, the back half must rotate in the opposite direction by exactly the same amount. This seemed to match Mary's photographs, but raised an even more perplexing question. How does the cat end up with its entire body rotated in the same direction? The cat-riding reflex presented a perfect scientific mystery, observable, repeatable, yet mathematically perplexing. As the 20th century dawned, it remained unsolved, awaiting new mathematical tools and technological capabilities that could finally reveal the secret behind this seemingly impossible feat of feline physics. By the 1930s, the paradox of the falling cat had evolved from a curious biological observation into a significant problem in the emerging field of topology, the mathematical study of properties preserved through deformations, twistings, and stretchings of objects. To understand why this feline ability suddenly captured the interest of mathematicians, we need to step back and consider what was happening in the world of physics during this period. The early 20th century had witnessed Einstein's revolutionary theories of relativity, the birth of quantum mechanics, and a complete reimagining of the fundamental forces of nature. Physicists were increasingly turning to abstract mathematics to describe phenomena that defied classical explanations. The cat-riding reflex represented exactly such a phenomenon, a seemingly simple physical action that defied explanation using Newtonian mechanics alone. In 1935, Dutch physicist Adriaan Fokker revisited the problem with fresh eyes. Studying slow-motion films of falling cats that offered greater detail than Mary's photographs, Fokker observed something crucial. The cat's rotation was not a single movement but a complex sequence of contortions. The feline does not simply twist, he wrote. It executes a specific choreography of movements, bending at the waist, pulling in its legs, and redistributing its mass in a precise sequence. This observation shifted the focus from a pure rotational problem to one involving the changing shape of the falling cat, its ability to deform its body during the fall. This was precisely the domain where topology could offer insights. The mathematical breakthrough came in 1969, when American mathematician Thomas Kane and Chinese physicist Min Shers published a landmark paper titled A Dynamical Explanation of the Falling Cat Phenomenon. Their work formalized what would become known as geometric phases in physics, the notion that when a system undergoes a cycle of changes in its internal configuration and returns to its initial shape, it may not return to its initial orientation in space. Their mathematical model demonstrated that by changing its shape in a cyclical manner, extending and retracting its legs, arching and straightening its spine, a cat could indeed reorient itself without violating conservation of angular momentum. The total angular momentum remained zero throughout the fall, but the cat ended up rotated. This was a profound insight that extended far beyond feline gymnastics. It suggested a whole class of phenomena in which motion could be generated without traditional propulsion, without pushing against anything. To visualize this concept, physicists developed an analogy that has become famous in its own right. The falling cat problem is mathematically similar to a swimming pool with no water. Imagine trying to swim in an empty pool. Intuitively, it seems impossible, there's nothing to push against. Yet, the mathematical models developed to explain falling cats suggested that certain motions could indeed generate displacement even in a frictionless vacuum. Russian physicist Rachel Shapiro, working at Moscow State University in the early 1970s, constructed a mechanical model to demonstrate this principle. Her geometric phase robot consisted of 3 connected rods that could change their relative angles. When the device executed a specific sequence of shape changes and returned to its original configuration, it had rotated in space, despite having no external forces acting on it. What we are witnessing, Shapiro explained in a 1972 lecture, is not a violation of physics, but rather a subtle exploitation of geometric principles that had not been fully appreciated in classical mechanics. The implications were staggering. If reorientation was possible without external forces, this opened new possibilities for controlling spacecraft in the vacuum of space, designing more efficient swimming robots, and understanding other biological systems that might employ similar principles. But while mathematicians and theoretical physicists had made significant progress, a complete explanation of how cats actually performed their aerial acrobatics remained elusive. The mathematical models were elegant, but did they truly capture what was happening in a real falling cat? To answer this question, scientists would need to bridge the gap between abstract mathematics and biological reality, a challenge that would lead to surprising collaborations between physicists, roboticists, and veterinary experts in the decades to come. In the summer of 1976, Dr. Naomi Burton, a veterinary researcher at Cornell University, received an unusual phone call from NASA's Jet Propulsion Laboratory in Pasadena, California. The caller, aerospace engineer Robert Snyder, had an odd request. He wanted to observe cats falling in a controlled environment. I explained to him that my ethics board would never approve deliberately dropping cats, Dr. Burton recalled years later in an interview. But when he clarified that NASA's interest was in developing better spacecraft orientation systems based on feline biomechanics, we found a compromise. That compromise resulted in one of the most peculiar research collaborations of the decade. Using high-speed cameras and motion capture systems originally designed for analyzing rocket launches, Burton and Snyder documented cats performing voluntary jumps from various platforms. The cats, wearing reflective markers at key anatomical points, leapt from perches of increasing heights into padded landing zones. What the NASA-Cornell collaboration revealed was extraordinary. The slow-motion footage, analyzed frame by frame, showed that cats execute their righting maneuver in distinct phases, each lasting mere milliseconds. First, the cat's vestibular system, inner ear, detects the sensation of falling and identifies which way is down. Second, the cat tucks its front legs and rotates its head and front shoulders toward the ground. Third, and most crucially, the cat arches its spine dramatically while simultaneously rotating its rear section in the opposite direction of the front. Fourth, the cat extends its legs to increase rotational inertia, completing the 180-degree turn. Finally, all four paws extend outward to absorb impact, with the spine flexing to further cushion the landing. The entire sequence typically completes in less than 200 milliseconds, faster than a human eye blink. The precision is astonishing, Burton noted in their published findings. Even kittens as young as 3 weeks can execute partial righting maneuvers, suggesting this is both innate and refined through development. What made this research particularly valuable was the identification of the exact biomechanical principles at work. The cat wasn't violating physics. It was masterfully exploiting physics through precise control of its body's moment of inertia, the distribution of mass relative to the axis of rotation. By tucking in its front legs while extending its rear legs, the cat created dramatic differences in rotational inertia between its front and back halves. This allowed the front to rotate quickly while the back moved more slowly, effectively creating a dynamic system where rotation could be transferred from one body segment to another. The NASA engineers were particularly interested in this principle of differential rotation. Space vehicles, which also operate in environments where external torque is limited, could potentially use similar mechanisms for orientation control. This would be especially valuable for small satellites that couldn't afford the weight penalty of traditional propellant-based attitude control systems. But there was still an apparent paradox. If angular momentum is conserved, how does the cat end up with its entire body rotated in the same direction? The answer lay in a counterintuitive mathematical fact. While the cat's net angular momentum remains zero throughout the fall, as physics requires, its shape changes create what mathematicians call holonomy, a change in orientation without a corresponding change in the system's overall momentum. To better understand this concept, physicist Richard Stevens of MIT developed what became known as the falling cat simulator in 1980, a computer model that applied Kane and Schur's mathematical framework to realistic cat anatomy. The simulator demonstrated that cats execute what amounts to a geometric phase change, similar to phenomena observed in quantum mechanics and other fields of physics where a system can return to its original configuration but with a changed orientation. What the cat accomplishes, Stevens explained, is a kind of physical sleight of hand. By changing shape in a precise sequence, It exploits the mathematics of rotation in a way that results in reorientation without violating conservation laws. The analogy that finally made this concept accessible to non-mathematicians came from an unexpected source: dance. In 1982, choreographer Nina Baker, after attending a lecture on the falling cat phenomenon, created a modern dance piece called Zero Angular Momentum, in which dancers demonstrated how controlled contortions could generate rotation even when starting from rest. Imagine holding a book in front of you with both hands, Baker would explain in her pre-performance talks. Without moving your feet, you can rotate the book 360 degrees simply by manipulating it in a specific pattern through three-dimensional space. The cat does something similar with its own body as the book. This dance analogy finally brought intuitive understanding to a phenomenon that had baffled scientists for nearly a century. But the story was far from over. As robotics technology advanced through the 1980s and beyond, engineers began to wonder, could we build machines that could perform this same feat? And what other secrets might nature have discovered long before human mathematics caught up? On a crisp autumn morning in 1988, in a laboratory at the Tokyo Institute of Technology, a small robot was about to make history. The device, ungainly by modern standards, consisted of two rectangular blocks connected by a triple-jointed mechanism. Named Nikobot, from the Japanese word for cat, it had no legs, no head, not even a power source while in free fall. Yet when dropped from an inverted position inside a padded chamber, it accomplished something remarkable. It flipped itself 180 degrees before landing. This was the world's first robot designed to mimic the cat riding reflex, created by roboticist Dr. Ryu Sato and his team after 5 years of development. We have created a machine that can reorient itself in free fall using only internal shape changes, Dr. Sato announced at the International Robotics Conference where the demonstration video was first shown. No propellers, no reaction wheels, no external forces, just pure geometric phase manipulation, exactly as a cat does. The achievement marked a turning point in the falling cat story. What had begun as a biological curiosity had evolved through mathematical theory and was now manifest in engineered reality. Nikobot proved that the mathematical explanations were not just theoretical constructs but practical, implementable principles. Yet Nikobot was painfully slow compared to its biological inspiration, taking nearly 2 full seconds to complete its rotation. A real cat could perform the same maneuver 10 times faster. What accounted for this difference? The answer came from an unexpected quarter: the world of competitive diving. Nancy Balthazar, a former Olympic diving coach turned biomechanics researcher, had been studying how human divers control their aerial rotations. Watching footage of Nikobot alongside cat videos and human divers, she identified a critical factor that the engineers had overlooked. The cat doesn't just change its shape, it also manipulates what we call the effective pivot point around which rotation occurs. Balthazar explained in a 1990 paper published in the Journal of Biomechanics. By sequentially activating different muscle groups in precise timing, the cat creates a dynamic system where the center of rotation itself moves through the body. This insight that the axis of rotation could shift position within the body during the maneuver proved crucial for the next generation of self-riding robots. By 1995, Dr. Sato's team had developed Nikobot 2, which incorporated microprocessors to control the precise timing and sequence of its shape changes. This version could complete a full rotation in under 0.7 seconds, still slower than a cat, but a dramatic improvement. Meanwhile, the mathematics of the falling cat problem continued to evolve in unexpected directions. In 1996, mathematician Roger Swanson at Princeton University established a formal connection between the cat riding maneuver and an esoteric concept in theoretical physics: gauge theory. Gauge theory, which undergirds much of modern physics from electromagnetism to the standard model of particle physics, deals with systems where physical behavior is unchanged under certain transformations. Swanson demonstrated that a falling cat's reorientation could be described as a gauge transformation in the configuration space of all possible cat shapes. What's remarkable, Swanson wrote, is that the same mathematical structure describing how quarks interact via the strong nuclear force also applies to how cats reorient themselves while falling. Nature appears to use similar mathematical patterns across wildly different scales and domains. This unexpected connection between feline biomechanics and fundamental physics sparked renewed interest in the problem across multiple disciplines. Biologists began examining whether other animals employed similar techniques. Marine biologists discovered that certain species of rays could execute in-water reorientations using comparable principles. Paleontologists proposed that some dinosaurs might have used related mechanisms for mobility. By the early 2000s, the falling cat problem had transformed from a curiosity into a central example of what scientists call embodied intelligence, the concept that physical form itself can perform computational functions. Rather than requiring complex brain calculations, the cat's ability to right itself emerges partly from the intrinsic properties of its body structure. The cat doesn't need to solve differential equations in its head, explained neuroscientist Dr. Richard Sullivan in a 2005 TED Talk that went viral. Evolution has encoded the solution into its physical form, its flexible spine, its distribution of mass, the neural reflexes that trigger the precise sequence of muscle activations. The cat's body itself is the computer solving this physics problem. This perspective shift, from seeing the cat-righting reflex as a paradox to recognizing it as an elegant example of embodied problem-solving, opened new avenues for robotics design and artificial intelligence. Rather than building machines that calculated every aspect of their movement, engineers began exploring designs where mechanical intelligence was built into physical structures themselves. The falling cat had become more than just a physics problem. It had evolved into a paradigm for understanding how nature solves complex challenges through the marriage of form and function. In 2011, at the Massachusetts Institute of Technology's Computer Science and Artificial Intelligence Laboratory, CSAIL, a team led by roboticist Natalie Byrne unveiled what appeared to be a lifeless, flexible cube, made of lightweight composite materials with no visible motors or power source. The device seemed unremarkable until it was dropped. As it fell, the cube suddenly came alive, its faces shifting and folding in a precise sequence. By the time it reached the crash pad below, it had transformed itself from random orientation to landing squarely on one specific face marked with an X. This was M-Cube Momentum Conserving Cube, the world's first passive self-orienting robot that required no power source during its fall. Using only stored elastic energy and a carefully calibrated triggering mechanism activated by the sensation of free fall, M-Cube demonstrated that the principles behind the cat-righting reflex could be implemented in forms radically different from biological anatomy. What we've created isn't just a robot that mimics a cat, Dr. Byrne explained. It's a new paradigm for designing systems that can reorient without propulsion, potentially revolutionary for space deployment, emergency devices, and any application where you need reliable orientation without power. The implications were immediate and far-reaching. NASA expressed interest in adapting the technology for planetary exploration drones that could survive being dropped onto distant worlds. Emergency management agencies explored applications for self-orienting medical supply packages that could be airdropped into disaster zones. The military investigated similar principles for guided munitions that could change direction without control surfaces or propulsion. But perhaps the most profound impact came in the theoretical realm, where the falling cat problem had ignited a renaissance in a field known as geometric mechanics, the study of how shape changes relate to movement through space. At Stanford University, mathematician Ross Sanchez had been developing what he called connection theory to unify various examples of geometric phase phenomena. His work demonstrated that the falling cat problem was just one instance of a broader class of physical systems where internal reconfiguration leads to external reorientation. We see this same mathematical pattern across remarkably diverse scenarios, Sanchez explained in a 2013 lecture. A spacecraft using internal reaction wheels to change orientation. A bacterium swimming through fluid by changing the shape of its flagella. A diver executing a somersault. All these systems exploit the same fundamental relationship between changing shape and changing orientation. This realization led to a powerful new conceptual framework called the Principal Fiber Bundle approach, which provided a unified mathematical language for describing all such systems. Using this framework, engineers could systematically design machines that generated specific movements through precise shape changes. The practical applications multiplied rapidly. By 2015, Researchers had developed submarine robots that propelled themselves not with propellers but through rhythmic shape changes, similar to how some jellies move through water. Aerospace engineers created experimental spacecraft that could adjust their orientation by shifting internal mass rather than firing thrusters. Medical researchers even explored tiny robots that could navigate through bodily fluids using cat-inspired geometric phase principles. Meanwhile, biologists using advanced imaging technologies made a startling discovery about feline anatomy that added another layer to the story. High-speed X-ray videos revealed that cats possess specialized neural circuits that activate specific muscle groups in precisely the sequence needed for the righting maneuver. These circuits appear to be partially hardwired from birth, explaining how even very young kittens can execute rudimentary versions of the righting reflex. It's a beautiful example of how evolution has encoded mathematical solutions into biology, noted veterinary researcher Dr. Nathan Barker in 2017. The cat doesn't understand gauge theory or geometric phases. It simply activates a pre-programmed neural sequence that triggers the right muscles in the right order. This insight led to a deeper question that bridged physics and philosophy. Had evolution somehow discovered sophisticated mathematics that humans only formalized in the 20th century? The cat righting reflex suggested that natural selection could indeed find solutions that exploit advanced physical principles, even without conscious understanding of those principles. By 2018, the falling cat problem had come full circle, from biological curiosity to mathematical puzzle to engineering inspiration and back to biology. Advanced computer simulations combining realistic physics with evolutionary algorithms demonstrated how the cat righting reflex likely evolved over millions of years, from primitive vertebrate movements to the extraordinarily efficient system seen in modern felines. What's remarkable, observed evolutionary biologist Rebecca Stewart, is that we can now simulate how natural selection might have optimized this behavior over evolutionary time. Our models suggest the modern cat righting reflex represents a nearly perfect solution given the constraints of vertebrate anatomy. The pinnacle of this renewed biological understanding came in 2019, when researchers using CRISPR gene editing technology identified specific genes involved in developing the neural circuits that control the righting reflex. These genes, it turned out, had analogs across many vertebrate species, suggesting that the fundamental building blocks for this ability might be widely distributed throughout the animal kingdom. The cat, it seemed, had not invented its remarkable ability from scratch. Rather, it had refined and perfected neural and biomechanical systems present in ancestral forms for hundreds of millions of years. In March 2022, astronaut Richard Summers floated inside the International Space Station's Japanese experiment module, preparing to conduct what many considered a trivial demonstration. Summers, a physicist by training and the first person to receive a PhD while in orbit, had convinced NASA to allocate precious crew time to what he called the zero-G cat experiment. The setup was simple: a specially designed flexible robot, roughly the size and shape of a house cat, equipped with an array of internal flywheels and actuators. Unlike previous self-righting robots designed for use in Earth's gravity, this device was specifically built to operate in the microgravity environment of space. We're about to witness something that directly connects a household pet to the future of space exploration, Summers announced to the camera as he released the robot into the center of the module. What happened next astonished even the engineers who had designed the system. The robot, initially motionless in space, began a series of undulating movements. Its spine arched and twisted, its limb-like appendages contracted and extended in sequence. Gradually, almost imperceptibly at first, it began to rotate. Within 30 seconds, it had completely reoriented itself and came to rest in a new attitude, hovering motionless once again. The Space Cat robot had just demonstrated what physicists call holonomic attitude control, the ability to change orientation in the vacuum of space without expelling any mass or interacting with external fields. It had accomplished this feat using only internal shape changes, directly applying the principles first observed in falling house cats over a century earlier. "This isn't just a curiosity," Summers explained afterward. "What you've just seen could revolutionize how we design spacecraft. Traditional attitude control requires thrusters or reaction wheels, both of which have significant limitations in terms of fuel consumption or mechanical failure points. This approach offers a new paradigm for long-duration missions where reliability is paramount. NASA's engineers had calculated that satellites using cat-inspired reorientation systems could extend their operational lifespans by up to 40% by reducing dependence on conventional attitude control systems that eventually fail or run out of propellant. The Space Cat demonstration marked a watershed moment in the falling cat story. The principles had now officially moved beyond Earth's gravity into the environment of space, fulfilling the theoretical predictions made decades earlier. But the journey from biological observation to space technology represented more than just clever engineering. It illustrated a profound shift in how scientists approached biomimicry, the practice of drawing inspiration from nature for technological solutions. The traditional approach to biomimicry has been largely superficial, explained Dr. Nina Blackwell, director of the Biomimetic Systems Laboratory at Stanford. We see a bird's wing and design an airplane wing, or observe gecko feet and create adhesives. But the falling cat phenomenon represents a deeper form of biomimicry, one that operates at the level of physical principles rather than just morphological features. This deeper biomimicry began influencing fields far beyond robotics and aerospace. In 2023, materials scientists unveiled a new class of programmable matter inspired by the cat writing reflex. These materials could change their macroscopic properties through microscopic reconfigurations, essentially applying the geometric phase principle at the molecular scale. One dramatic application emerged in architecture, where engineers developed building components that could reorient themselves during earthquakes to minimize structural stress. These adaptive load distribution systems contain no motors or power sources. Instead, they used the earthquake's own energy to trigger a precisely calibrated sequence of shape changes that redirected forces away from critical structural points. It's exactly analogous to how a cat redistributes momentum during a fall, explained structural engineer Roy Simmons. The building isn't fighting the earthquake, it's dancing with it, using the energy to reconfigure itself into a more resilient form. Perhaps most surprisingly, the mathematics developed to explain falling cats found application in quantum computing, where researchers discovered that certain quantum algorithms could be visualized as geometric phases in high-dimensional configuration spaces, conceptually similar to the transformations executed by a falling cat. There's something almost mystical about finding the same mathematical structures in quantum computation that we see in a falling house pet, noted quantum physicist Dr. Nadine Blake. It suggests a deep unity in how nature processes information across wildly different scales. By 2025, geometric phase engineering had become a recognized discipline spanning multiple fields, from robotics and materials science to quantum information theory and even financial modeling. At its core was the insight, first hinted at by a falling cat, that shape changes could be harnessed to produce directed motion without traditional propulsion. As the falling cat story approached its 150th anniversary since Mary's first photographs, the problem that had once seemed like a mere curiosity had transformed our understanding of motion itself. What began as a paradox, how can a cat rotate in free fall without violating conservation of angular momentum, had evolved into a profound insight that the relationship between shape and motion is far richer and more nuanced than classical physics had suggested. The humble house cat, it turned out, had been exploiting a sophisticated loophole in Newtonian mechanics all along, not violating the laws of physics, but revealing their subtle complexities that had remained hidden until we knew exactly how to look. In the final analysis, what does the physics of falling cats teach us about the universe and our place within it? Perhaps the most profound lesson lies in what we might call the principle of embedded wisdom. The idea that nature often solves complex problems by encoding solutions directly into physical form, rather than through explicit calculation. A cat doesn't solve differential equations to right itself during a fall. It doesn't understand the mathematics of geometric phases or the conservation of angular momentum. Yet, through millions of years of evolutionary refinement, it has developed a system partly anatomical, partly neurological, that perfectly exploits these mathematical principles. This suggests a deeper truth about intelligence itself, that cognition need not be centralized or explicit. The wisdom of the cat's solution exists not in its brain alone, but is distributed throughout its entire physical being, in the precise ratio of mass between its front and rear segments, in the flexibility of its spine, in the neural circuits that coordinate the precise sequence of muscle activations. What we call intelligence in living systems often resides as much in body as in brain, observed cognitive scientist Richard Solomon in his landmark 2024 paper, Embodied Mathematics, From Cat Writing to Cognitive Foundations. The falling cat reminds us that knowledge can be encoded in form and function, a lesson with profound implications for artificial intelligence, which has historically emphasized computation over embodiment. This perspective offers a humbling reminder of how much wisdom exists in the natural world. Solutions perfected over evolutionary timescales that human engineers are only beginning to understand and emulate. The cat discovered its remarkable writing ability millions of years before human mathematicians formalized the principles that explain it. Yet simultaneously, this story showcases humanity's unique capacity to abstract and generalize from specific examples. By observing a falling cat, developing mathematical models to explain its motion, and then applying those models to entirely different domains, from spacecraft to quantum computing, humans demonstrate an ability to extract universal principles from particular cases. As we stand at the intersection of biology, physics, mathematics, and engineering, the falling cat phenomenon reveals something profound about the nature of discovery itself. Sometimes the most significant insights don't come from looking outward to the cosmos or inward to subatomic particles, but from careful observation of the ordinary miracles that surround us daily, like a cat always landing on its feet. The cat's solution, elegantly simple yet mathematically sophisticated, reminds us that the universe operates according to consistent principles across all scales, from the quantum to the cosmic. The same mathematical structures that describe a falling pet also apply to spinning neutron stars and quantum particle interactions. This unity suggests a deep coherence to reality that transcends the artificial boundaries between scientific disciplines. Perhaps most poetically, the falling cat demonstrates that constraints, in this case, the conservation of angular momentum, don't just limit possibilities. They can also inspire creative solutions. The cat doesn't overcome the laws of physics. It dances with them, finding possibility within constraint. And therein lies the ultimate lesson. In a universe governed by immutable physical laws, freedom comes not from breaking the rules, but from deeply understanding them and discovering the hidden spaces where creativity can flourish. From Mary's first photographs to space station demonstrations, from mathematical paradox to engineering breakthrough, the falling cat has taken us on a journey across disciplines and centuries. What began as a simple question, how does a cat always land on its feet, opened a window into the fundamental nature of motion, the relationship between shape and orientation, and the embodied intelligence that permeates the living world. We look at a falling cat and see not just a pet performing an acrobatic trick, but a living embodiment of mathematical elegance, a four-legged teacher of physics principles, and a reminder that some of nature's most profound secrets hide in plain sight, waiting for us to ask the right questions.